Okay, AP Biology, sorry about that. My video cut me off at 15 minutes, and so instead of rushing through this last section in 30 seconds, I thought I would do a video part 2. So, picking up here, we are on the downward track of the action potential, and so now we are going through a repolarization phase. So what that means is that we are now becoming the inside of the cell is now becoming more negative as respect to the outside. So we're kind of going back to that normal voltage difference. Inside negative, outside positive. Okay, so if you remember, what we've done so far is that the sodium channels have opened. The sodium rushes from the outside of the cell to the inside of the cell, causing the membranes to change voltage. So the outside of the cell becomes negative and the inside becomes positive. That change in potential is called depolarization, and that is the upward trend on the graph that we see. And once we have a change in that voltage, that is now going to stimulate the potassium channels to open, and so then the potassium ions are going to move from the inside of the cell to the outside. But the potassium channels are open almost 3 times longer than the sodium channels are open. So that gives it a chance to move more potassium ions out of the cell than we were able to move sodium in. So what does that mean? Well, that means if we take a look at our graph here, this part of the graph is showing that potassium is moving out of the cell, causing the inside of the cell then to become, again, got to find out where to put me here. We're going to go over here in the corner. All right, so as we move the potassium ions out of the cell, that is going to cause that membrane potential to revert back to normal, which means the inside is going to come down, 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 and become more negative. Okay, but because those potassium channels are open so much longer than sodium, we are able to move more sodium ions out than we did. Gosh, I keep messing up with that. We are able to move more potassium ions out than we moved potassium in. And so then what we see is that this graph then is going to drop down below where our resting potential was. It's actually going to become more negative than what we really want it to be. And this is what we refer to as hyperpolarization, or it is more polarized than what we started off with. Okay, let's move me again. All right. So hyperpolarization, we have repolarization overshoots the resting potential to about negative 90 millivolts, and this is what is referred to as hyperpolarization. Its importance is it prevents the neuron from receiving another stimulus during this time, preventing any stimulus already sent up the axon from triggering it in the opposite direction. Remember, in order for us to trigger an action potential, our threshold has to be reached. So we have to get that voltage to change up to negative 55. So we are now farther away from that. So it's going to take a really big stimulus to get that to change. Our gradients are all messed up. So really it's virtually impossible to stimulate another action potential in that section of the neuron until we get everything kind of back to normal. Okay. All right, so again, here's our hyperpolarization. So what we need to do is we need to get that voltage right back up here to that negative 65. All right, so how are we going to do that? Well, we have the pump. We've allowed the sodium potassium to switch places. However, it has not switched in terms of reaching equilibrium. We've just allowed it to move and kind of upset the balance. And so we still have a high amount of sodium outside and a high amount of potassium inside. And so in order for us to get that back to that negative 70 millivolts, then what we need to do is we're going to have to start pushing these ions and forcing them to go against that gradient. This is where we see the active transport take place, which is that we are going to now push these ions against their gradient, and that is going to require energy. Okay. And the way that we use this is we can't use these channels anymore with the gates on them. We can't use open channels. We now are going to have to pump them across. So we have a thing that is called the sodium-potassium pump, and they are very specific to these two ions. So the sodium and the potassium pump are going to be working so that they pump 3 sodium ions out and 2 potassium ions in. And this is working very similar to the clothesline pins that you were using yesterday, where they have different shapes that are going to fit specifically with the ions they are associated with. And so as they open in one direction, they will spit the ions in this case potassium in. They will hang on to the receptor areas for the sodium will open up and sodium will attach. Because it's using energy, we see this P. This is coming from ATP. We'll go into that a little bit later, but remember ATP is our energy molecule. This is going to cause that pump to change places or change shape, which will open up so that the sodium can go outside the cell. And so really what this is doing then is it is resetting the gradient with more sodium outside, more potassium inside, and so that we really have that difference of negative 70 millivolts between the outside and the inside of the cell. Okay, this is what is reestablishing that gradient and setting us up so that we can go through that action potential again. Okay, so this is the section that we're dealing with right here. This is getting things back to normal. Okay, this is our hyperpolarization, and we are resetting to normal, to resting. All right, a couple things to know about an action potential is that it either happens or it doesn't happen. There is no, oh, I think I'm going to do this, and we're going to go halfway down the axon, and then we're going to quit. Once the first domino is knocked over, or the first sodium gates are knocked over, and we have reached that threshold, every other sodium and potassium channel will open when it is triggered all the way down. Okay, and so we call this an all or none principle. So we either open them all or we shut them all, but it's not going to be any of this kind of petering out halfway down the axon and then not resulting in any reaction. Okay, all right, so let's take a look at this again. This is the last little graph here. We'll see it all in completion. All right, so when we take a look at the graph here, we have a stimulus that comes in, but it really wasn't much because it didn't hit the dotted line. Remember, the dotted line is the threshold. So let's try this again. Oh, there's another graded potential. So we got a little stimulus, just not enough to activate anything. All right, next one, here we go. We've hit that threshold. So what's going to happen? We are going to go up. All those sodium gates are going to open, and we're going to flood the inside of that cell with sodium ions, and our graph is going to shoot up. Okay, so remember, our sodium ions are open, or sodium channels are open here, 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 here. When we get to this apex here, the sodium channels become blocked, okay, with that ball and socket, ball and chain model, and our membrane potentials are going to swap places, more positive on the inside and negative on the outside, which stimulates the sodium channels to open, the potassium channels to open. The potassium channels are going to open and allow potassium to leave the cell, which is going to cause those membranes to become more and more negative again. So this is repolarization. But because the potassium channels are open so long, they go down below the resting, which is called hyperpolarization. And in order for us to have another action potential, we need to reset. And so we see that the sodium-potassium pump is activated, and we're going to move 3 sodiums out to 2 potassiums in to get us back to this resting membrane potential. All right, I know that's really confusing, but hopefully with the activities in class and my awesome lecture here, let's go right in the middle of the screen. There you go. Hi, from China. This is Mrs. Warren. Goodbye.